So our next question, our next talk is from Nicolas Laporte. So if you want to get your slides up, yep, that looks great. So take it away, Nicolas.
Okay, thank you, Charlotte. And first of all, I would like to thank the organizer to give me this opportunity to talk at this very nice conference. Today, I'm going to focus on the result from my last paper, and you have here the archive number on this first slide. You also have the name of the main people involved in this project. And the main goal of this project was to probe cosmic dawn by observing the most distant galaxies. So here I'm showing you pictures. We are all familiar with these pictures, summarizing the history of our universe. And I'm mostly interested by this period, which happened 300 million years after the Big Bang. That's the formation of the first galaxy. Typically, that's cosmic dawn. So that's just before the epoch of reionization. So how can we probe cosmic dawn with the most distant galaxies? Well, I think you have two different approaches. You have the direct approach, where you can use the deepest data you have and try to see how far you can go in redshift and still detect galaxies. So we can do that typically with the Webb Space Telescope, and we had just before a very nice talk by Guido trying to search for galaxy at redshift up to redshift 12, because that's the Webb Space Telescope limit. I'm not going to discuss this approach. I will focus on the indirect approach, which is if we search for extremely distant galaxy and we try to determine the age of this distant galaxy. And with that, you will be able to push back in time the formation of the first galaxy. But to do that, you need to answer three questions. First, do we have good age indicators at very high redshift? Secondly, can we measure the age of all the galaxies at very high redshift? And then, do we have any good example of galaxy with an old stellar population at a redshift above 8, for example? So, first of all, I would like to give you my definition of the age of a galaxy, and I'm sure that my definition will be completely different from the definition of a terrorist or people working on simulation. So my definition of the age of the galaxy is the period during which a galaxy is forming stars. And do we have good age indicators? I would say that we have at least two age indicators. First, we can use the dust content of high redshift galaxy, because if you can estimate the amount of dust you have in a galaxy, and if you assume some dust production rate by stars, you can get a first estimate of the age of a galaxy. I'm not going to discuss this during this talk. I will focus on the other age indicator, which is the constraint of the size of the Balmer break. And as you can see here, you have a plot showing you the evolution of the Balmer break as a function of the age of the stellar population. And as you can see, if you increase the age of the stellar population, you also increase the size of your Balmer break. So the good point is that at redshift above 8, this Balmer break is seen between the two first IRAC channels, so between 3.6 and 4.5 microns. But as we know, at very high redshift, we can see break, not due to stellar continuum, but due to strong emission line. And this is what you can see here. For example, in this galaxy there, you see that you have a break at between 3.6 and 4.5 micron, but this break is due to strong emission line. And this is summarized in this plot, where you have, as a function of redshift, the Spitzer colors. And as you can see, at redshift above 7, so we are in situation number 2, so somewhere here, we have strong emission lines, such as oxygen 3 and H beta in the 4.5 micron channel. So if you want to be free from contamination by strong emission line, you need to search for object at a redshift above 9, so to be in that situation, number 3, somewhere here. So that's the selection. That's one of the selection criteria we use to identify galaxy with an old stellar population. So first we look for bright object, relatively bright object with an H-band magnitude less than 26.5 AB. We ask for relatively large IRAC colors, so at least 0.5 magnitude, and of course a photometric redshift above redshift 9.1. We search for galaxies in the CANDLES, UltraVista, and Frontier Field survey. And now we should ask ourselves the question, is the Balmer break a good age indicator? And to answer this question, I would like to show you this plot, where you have the evolution of the Spitzer colors, so 3.6 minus 4.5 micron, as a function of the reddening, so typically of the dust content of a galaxy. Because as we know, the Balmer break can be influenced, let's say, by the dust content of a galaxy. So if we ask for at least 0.5 magnitude for the Balmer break, and if we remove all the old stellar population solution, the color bar here is typically the age of your stellar population. So you see that if we remove all the old stellar population, let's say all the solution with an age larger than 20 megayear, then we need a reddening of at least 1.7 magnitude, which is a huge reddening at high redshift. And so far, we don't have any evidence that in these galaxies at very high redshift, redshift 8, 9, 10, that these galaxies host a huge amount of dust. We have some examples of galaxies with dust, but this is not the global properties of the population at very high redshift. So I think at very high redshift, constraining the size of the Balmer break is a good method to determine the age of a galaxy. So here you have the sample we selected. So this is 6 objects. We use one of these subjects, this one, GD1, nearly 3 years ago as a pilot program, and to try to identify if the break we can see between 3.6 and 4.5 micron is due to an old stellar population. And as you know, we detected oxygen-3, 88 micron with ALMA, Lyman alpha with the VLT, and by doing some SED fitting, we can demonstrate that the break we have here is due to the old stellar population. So, of course, after these results, we ask ourselves, is this subject a representative of the general population, or is it just an outlier? So to try to answer this question, first we use simulation, and we work with, this is the work we did with ARLICAT. So we use a small box, something like 70 co-moving megaparsec cube. And within this small box, we identify 3 objects like the one at redshift 9.11 I just discussed. So it means that these objects are not rare, and we should search for this object in all the survey we have. So that's why we combine 70 hours of telescope time, combining data from all the telescope you have on this slide. Why do we need to do some spectroscopic follow-up? Because we want to know, to measure precisely the redshift of our galaxy. Because if the redshift is below 9, then that would be complicated to claim that the break we see is due to the continuum and not to contamination by emission line. So we combine data from the VLT, from Keck, MOSFIRE, from Gemini, and from ALMA. And I'm going now to show you the results. So the first result is from ALMA. Here I'm showing you the detection of an emission line here that we believe is oxygen-3 at 88 micron at a redshift of 9.28. So this is completely consistent with the photometric redshift. So here you have the 1D spectra, and here you have the shape of the line. We can't see any evidence for a rotation for this line. Here you have the plot showing you the pixel signal-to-noise ratio distribution, where a peak here at signal-to-noise ratio of 6, which is consistent with our detection. Here you have the result from our near-infrared spectroscopic campaign looking for Lyman alpha and other emission lines. And as you can see, we have very few success. We have no detection for the object for which we detect oxygen-3 at redshift 9.28, nothing in the ultra-vista object, and maybe a faint detection in one of the Goods North objects. But for the rest of the talk, I will consider this subject as a non-detection. But we have a detection, at least in these subjects in Goods North at a redshift 8.8. Okay, so if I combine all these data, I'm going now to the conclusion of this work. The first conclusion is the fraction of detected Lyman alpha as a function of redshift, because as you know, when we enter into the epoch of ionization, so at redshift above 6, we should have a strong decrease in the number of detected Lyman alpha. But if we consider just our object, our sample, and I agree with you, our sample is biased because we are just looking for objects with evidence for an old stellar population. The detected fraction of Lyman alpha is not 0, is let's say something like 40%, right, with huge error bars. So I think this result supports the hypothesis of an old stellar population in all these subjects. Conclusion number 2 is the formation redshift for all these galaxies, for the 6 galaxies in our sample. So we use BAGPIPES. We did some SED fitting using several realistic star formation history. Here you have the list of the star formation history we use. I'm not going to enter into detail. Here you have an example of SED fitting. And as you can see here, we can see the Balmer break, or at least that's the solution preferred by the SED fitting work. And all these galaxies have a formation redshift above 15. Right? And you can also look at the last column here, which is the fraction of mass formed in this galaxy at a redshift above 10. And as you can see, 70% of the mass in most of the galaxy is formed at a redshift of 10. So now the third conclusion of this work is that you can take the star formation history of your object, convert the star formation history into UV luminosity, and demonstrate that these galaxies, the progenitors, let's say, of this galaxy, will be easily detected by the James Webb Space Telescope. Here I'm showing you the near-cam sensitivity. This is in 3 hours, the 5 sigma sensitivity. And as you can see, we will detect easily all these objects. And the last conclusion from this work is when you try to study the evolution of the mass fraction as a function of redshift, to try to distinguish between the two evolution we have, the debate we have in the evolution of the star formation rate density. Do we have a smooth decline or do we have a rapid decline of the star formation rate density? And of course, this will give you different evolution for the mass fraction evolution. And as you can see here, that's the red curves you have there. We are, let's say, more consistent with the rapid decline. This is what you have there. So I think I have no time to discuss this, but if we have evidence for Balmer break in galaxy at redshift above 9, then it means we should have Balmer break or all stellar population in galaxy at redshift below 9. And this is a work done by Guido Roberts-Bersani. I encourage you to read the paper where we show that if we combine HST, Spitzer, and ALMA data, we are able to identify this Balmer break in galaxy at redshift below 9. And I think I'm running out of time, so I leave you with my conclusion and I'm taking questions. Thank you.
Thank you very much, Nicolas. So if we'll just wait a few seconds for some questions to come in. So reminder, you can post your questions to Nicolas in Slack, and especially encourage early career researchers to ask questions.
Right, we got the first question from Rohan Naidu. So could you elaborate on your argument about how Lyman alpha detections, non-detection supports the stellar population being old?
True. Well, the idea is just to say that if we are at redshift, let's say 9 or 10, and if we detect Lyman alpha, it just means that the galaxy had time to ionize the neutral hydrogen in its surrounding, right? So this is the argument. If you can detect Lyman alpha, it just means that the galaxy had time to ionize the neutral hydrogen in its surrounding. That's it. So if you can detect Lyman alpha in such high redshift object, that's one hypothesis.
Okay, I'm going to ask a question from Justin Spilker. So he asks, how worried are you about potentially non-uniformly distributed dust? For example, could clumpy dust produce the red SEDs and mimic the Balmer break, but remain undetected by ALMA?
Yeah, that's a good point, actually. But when we stack, I think I've read many studies where you have people stacking the ALMA detection or the ALMA continuum, and they still detect nothing. And I think even if you have clumpy dust, you should see the dust in a stack at redshift 8 or 9, right? So the idea will be that dust, I mean, that would be my answer. We know that the amount of dust in high redshift, in redshift 8, 9, or 10 object is not sufficient to change or to influence the shape of the Balmer break.